I can give you smaller and smaller pieces forever, each one shrinking towards zero, and somehow their total still grows past every number you name. Watch the yellow bar. I add one whole unit, then a half, then a third, then a fourth. The pieces get embarrassingly tiny. The total crosses 2. Keep going, and it crosses 3. Given enough time, it crosses 100, a million, whatever target you put in front of it. There is no ceiling. That claim feels illegal, because the pieces plainly approach zero. And yes, every individual piece eventually becomes too small to see. Still, the pile never settles. This is the harmonic series, 1 plus 1 half plus 1 third plus 1 fourth, continuing forever. I got the intuition wrong the first time I met it. I thought, well, zero-sized pieces should eventually stop mattering. That sentence hides the entire trick. They never become zero. More importantly, shrinking terms can shrink at very different speeds. Some shrink fast enough for their total to finish. These do not. The reason is hiding in a picture where we deliberately make most of the terms smaller. That sounds like the worst possible strategy, which is exactly why it works. Keep your eye on the growing bar, because we are about to throw away a lot of its length and prove it still cannot be contained. The first mystery clears up quickly. Terms going to zero only gives a series permission to converge. It does not force convergence. Here is the clean reason. Suppose an infinite sum really does settle at some finite number, call it S. Its partial totals S1, S2, S3, and so on must crowd closer and closer to S. The new term is the gap between two neighboring totals. A sub n equals Sn minus Sn minus 1. If both totals are squeezing toward the same destination, that gap has to shrink toward zero. So a convergent series must have terms approaching zero. Necessary condition, one-way implication. The arrow does not automatically point backward, which is a very common mathematical booby trap. If the terms fail to approach zero, we can reject convergence immediately. If they do approach zero, the test just shrugs. Our harmonic terms pass this test. Because 1 over n approaches zero, they have cleared the lowest possible bar. Congratulations to them, I guess. We still need to know whether the total settles. And looking at the first few partial sums will not rescue us. They grow painfully slowly. After 10 terms, the sum is only around 2.93. After 100, around 519. After a million, barely over 14. That slowness is excellent camouflage. So how can we prove endless growth without wading through a million microscopic additions? We stop inspecting terms one at a time. Grouping the terms exposes something the decimal totals are trying very hard to hide. Leave the first term alone. Then group the next one term, the next two terms, the next 4, the next 8. Every group doubles in size. So the blocks are 1 half, then 1 third plus 1 fourth, then 1 fifth through 1 eighth, then 1 ninth through 1 16th. Now watch the denominators inside each block. In the block ending at 1 eighth, every term is at least 1 eighth. There are 4 terms. 4 copies of 1 eighth make 1 half. The actual block is larger than that because 1 fifth, 1 sixth, and 1 seventh all beat 1 eighth. Same trick in the next block. 8 terms, and every one is at least 1 16th. That block contributes at least 8 sixteenths. Again, 1 half. Every doubled block adds at least another half. Forever. This is the screenshot picture. The pieces shrink, yes, while the number of pieces in each block grows at exactly the rate needed to cancel that shrinking. Half, 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 with no final block. We even replace most terms by smaller ones, and the simplified sum still contains infinitely many halves. So the original sum must diverge. That is the answer in one frame. But there is a detail worth poking. Why did powers of 2 fit so perfectly? And what does this picture tell us about how slowly the divergence happens? Powers of 2 work because doubling the denominator roughly halves each term, while doubling the number of terms available. Those changes balance. Between n equals 8 and n equals 16, we collect 8 terms of size around 1/16. Between 16 and 32, we collect 16 terms around 1/32. Each doubling buys roughly the same amount of total growth. That gives us a strange clock for the harmonic series. Ordinary time counts terms 1, 2, 3, 4. The useful clock counts doublings 1, 2, 4, 8, 16. On that clock, the sum climbs by about a fixed amount each tick. To force the total up by another 1/2 using our crude bound, the number of terms has to double. To gain 10 more units, we may need around 20 doublings. That means multiplying the term count by about 1,000,000. Slow, ridiculously. Finished, never. This also explains the numbers from a moment ago. 1,000,000 terms only contain about 20 doubling blocks. So a total around 14 is not surprising. Infinity does not care that the growth is inconveniently slow. It has unlimited doublings to spend. There is a more precise statement hiding here. The partial sum up to n behaves a lot like the natural logarithm of n. The word logarithm sometimes arrives wearing a fake mustache and pretending to be complicated. Here it simply counts multiplicative growth. Why should the area under 1 over x know the same secret as our blocks? The curve gives the same verdict, and it tells us how fast the total grows. Draw equals 1 over x. Now build a staircase using rectangles of width 1. Over the interval from 1 to 2, use height 1. From 2 to 3, use height 1/2, then 1/3, 1/4, and so on. The rectangle areas are exactly the harmonic terms. Because 1 over x decreases, these left edge rectangles sit above the curve, so the harmonic partial sum is larger than the area under the curve over the same stretch. That area is the integral of 1 over x, which equals the natural logarithm. From 1 to n plus 1, the area is log of n plus 1, and log n keeps growing without bound. Slowly, yes, but without bound. Therefore, the staircase total cannot settle either. There is also a lower staircase giving an upper comparison, so the sum is trapped close to log n. More precisely, log of n plus 1 is no greater than h sub n, and h sub n is no greater than 1 plus log n. Our block proof gave divergence with almost no calculus. This picture adds scale. If you want the harmonic sum to increase by about 1, n must be multiplied by e, roughly 2.718. That is wonderfully rude behavior. Constant additive progress demands exponential patience, yet the staircase stays slightly above the logarithmic area. That leftover gap does something unexpected. It does not grow forever. It settles. That leftover gap approaches a constant about 0.57721. It is called the Euler-Mascherny constant, usually written gamma. Nobody knows whether gamma is rational. Honestly, this constant has been sitting in a very basic staircase for centuries and still refuses to show us its fraction status. Slightly dramatic for a gap between rectangles, but fair enough. The useful formula is h sub n equals log n plus gamma plus a small error that vanishes as n grows. So at 1,000,000 terms, log of 1,000,000 is about 13.8155. Add gamma and we get roughly 14.3927, matching the actual harmonic total. Divergence now has a speedometer. To reach a total of 100, n needs to be approximately e raised to the power 100 minus gamma. That term count has 43 digits. If you added 1,000,000,000 terms every second, the universe would have to wait an offensively long time. But finite waiting time is beside the logical point. For any target height, there is some finite n that gets past it. The target can be absurd. The needed n can be worse. It still exists. This distinction between unbounded and fast matters all over analysis. A sequence can wander upward so slowly that every practical experiment suggests a ceiling. The harmonic series is the mascot for that trap. Now we should ask the reverse question. If approaching zero is too weak, how much faster? Must the term shrink before the infinite sum finally fits inside a finite box? A tiny change in the exponent completely changes the ending. Consider 1 over n to the p. When p equals 1, we have our harmonic series and it diverges. Set p equal to 2, and the terms shrink faster. Now the total converges. In fact, it lands on pi squared over 6, which feels like pi wandering into the wrong meeting. But we will leave that mystery alone today. The full rule is sharp. The sum of 1 over n to the po converges when p is greater than 1 and diverges when p is less than or equal to 1. Assuming positive p for the shrinking term story, the area picture makes the border visible. The integral of x to the negative p has an antiderivative involving x to the 1 minus p. If p exceeds 1, that power drops towards 0, leaving finite area. If p is below 1, it grows. Right at p equals 1, the ordinary power formula hits a division by 0, and the logarithm appears. That border case is our stubborn series. Keep your eye on the tail of the graph. At p equals 1.1, it looks almost identical to 1 over x for a long time, yet its infinite area is finite. As p slides down toward 1 from above, the total blows up. Convergence can be that sensitive, so exponent size gives one answer, but real sequences do not always arrive as neat powers. We need a test that asks a more physical question. How much mass survives at each scale? The grouping proof was secretly measuring mass per scale. Take any positive decreasing sequence. Look at indices from 1 to 2, 2 to 4, 4 to 8, and onward. Each scale contains about twice as many terms as the previous one. Ask whether the typical term falls by more than a factor of 2, less than a factor of 2, or almost exactly 2. For 1 over n squared, doubling n makes each term about 1/4 as large, while the block gets only twice as crowded. So each new block carries about half the mass of the previous block. Those block totals form a geometric series and finish. For 1 over n, doubling n halves the term while doubling the crowd. The block mass stays roughly constant. Divergence. For 1 over the square root of n, terms only fall by a factor of square root 2 while the population doubles, so block mass grows. Very divergent if we are allowing that phrase. This scale view is called Cauchy condensation when written as a theorem. For positive decreasing a sub n, the sum of a sub n and the condensed sum of 2 to the k times a sub 2 to the k either both converge or both diverge. The condensed version samples one term per doubling and compensates for the term skipped. For a sub n equals 1 over n, every condensed term equals 1. That is about as divergent as a diagnostic can look. And this machine can handle sequences that sit right on the harmonic boundary with extra logarithms attached. Here is a series that shrinks faster than the harmonic series and still diverges 1 over n log n, starting at n equals 2, so the logarithm behaves itself. The extra log in the denominator does make every term smaller. It just does not make them small enough. Condense it. At en equals 2 to the k, the term is 1 over 2 to the k times log of 2 to the k. Multiply by the block size 2 to the k, and those powers cancel. What remains is 1 over k log 2. That is a constant multiple of the harmonic series, so it diverges too. We added a factor that grows without bound to the denominator, and infinity still wriggled out. This was one of those facts I had to calculate twice because my intuition filed a complaint. Add another logarithm, 1 over n log n times log n, still diverges. Keep nesting logs and the boundary keeps moving in this peculiar way, but square the first logarithm, giving 1 over n times log squared n, and the series converges. The integral test shows why. Substitute u equals log x, and the integral becomes 1 over u squared, which has finite tail area. For 1 over n log n, the same substitution gives 1 over u, returning us to the original harmonic problem in disguise. The harmonic series is apparently capable of wearing smaller harmonic series as hats, so term size alone can mislead, even when we compare two formulas. Can signs rescue a series whose absolute sizes still carry infinite mass? Signs can rescue the total through cancellation, take 1 minus 1 half plus 1/3 minus 1/4, continuing with alternating signs. The term magnitudes are still harmonic, so their absolute sum diverges, yet the sign total converges and it lands on log 2. Watch the partial sums bounce. The positive additions push above the destination. The negative additions pull below it. Since the step sizes decrease towards 0, the overshoots become smaller and smaller. Odd partial sums descend, even partial sums rise. They squeeze the same number between them. This does not contradict anything we proved, because our grouping argument relied on every term being positive. With positive terms, partial sums can only climb, and cancellation is unavailable. Alternating signs create a second mechanism, besides fast shrinking. Opposing errors erase one another. The order now matters in a way it did not for positive terms. Rearrange a conditionally convergent series carefully and you can force it toward a different total, or even make it diverge. That result is real, and it is deeply impolite. We will keep the terms in their original order here. The comparison exposes the core issue. Both 1 over n and negative 1 to a power over n have terms approaching 0 at exactly the same rate. One accumulates infinite positive mass, the other balances that mass through signs. Therefore, the sentence, "the terms go to 0, omits two crucial pieces of information, the rate of decay and the pattern of cancellation. There is one more misconception to clean up. What does an infinite sum actually mean if nobody ever performs infinitely many additions? An infinite sum is a claim about finite sums. We never reach an infinity, the addition. We define h sub n using the first n terms. Then ask what happens as n grows without bound. If those finite totals approach a finite number, the series converges. If they exceed every fixed ceiling, the series diverges to infinity. That language matters because people sometimes imagine infinity as a gigantic final index where the terms have become 0. There is no final index, and 1 over n is positive for every finite n. Pick a ceiling m. Our block proof gives a construction. After enough power of 2 blocks, each worth at least 1/2, the partial sum exceeds m. Specifically, after 2m blocks, their contribution alone reaches at least m. Ignoring the first term and any extra amount, the corresponding number of terms is enormous, around 2, raised to 2m, but finite. This is the quantifier machinery under the hood. For every target m, there exists a finite n, such that h sub n is greater than m. Swap those phrases and you get a very different statement. There exists an n that beats every m would demand one finite total larger than all numbers, which is nonsense. Analysis contains a surprising amount of keeping for every, and there exists, in the correct order, tiny words, huge consequences. Now that the logic is clean, we can return to the physical picture and ask exactly where the naive intuition broke. The naive picture watches one dot and forgets the crowd. Yes, the nth term has size about 1 over n. Around index n, though, there are roughly n nearby terms on the same scale. Multiply size by population. N terms times 1 over n each gives order 1 total mass. That is the whole phenomenon in a sentence. At every larger scale, the individual pieces become weaker, while the scale contains proportionally more of them. Neither side wins. For 1 over n squared, n pieces near size 1 over n squared contribute about 1 over n, so later scales fade away. For 1 over the square root of n pieces near 1 over square root n contribute about square root n, so later scales get heavier. The harmonic series balances exactly on the border. This way of thinking appears far beyond series. Probability distributions can put tiny probabilities on an enormous number of outcomes and still leave substantial mass in the tail. Algorithms can perform cheaper operations more frequently and accumulate a large cost. In physics, a weak effect spread across enough space can remain important. Same accounting problem, amplitude times abundance. Watch this one dot shrink, it looks harmless. Now, zoom out and reveal the doubling crowd around it. That zoom is what the phrase "goes to 0" fails to include. We finally have the intuitive repair. But I want to finish with a nastier sequence because it shows that even fast-looking decay can be staged to fool almost any finite observation. A sequence can behave beautifully for an absurdly long time, then reveal that its total still diverges. Build it in plateaus. For the first huge block, make every term tiny. For the next vastly longer block, make each term even tinier, but choose enough terms that the block total is 1. Repeat. The individual terms decrease towards 0. Every visible term may look far smaller than the harmonic terms around it, yet each hidden plateau contributes another full unit, and infinitely many plateaus force divergence. This is why checking a trillion terms cannot prove convergence. Finite data only sees a finite prefix. The tail owns the verdict. The harmonic series is kinder because it follows a clean formula and exposes its structure under doubling. Still, the lesson survives. 0 is a local statement about individual terms. Convergence is a global statement about accumulated mass across the entire tail. Those are different jobs. Our original mystery came from asking the local fact to perform the global job. The repair is to track mass by blocks, compare with an area, test a decay rate, or identify cancellation. And now the loose thread that still bugs me. The harmonic sum grows like log n, with that stubborn extra gamma sitting between the staircase and the curve. We understand exactly why the sum escapes every ceiling, yet that little 0.57721 gap still will not tell us whether it is a fraction. Infinity was the easy part. The leftover dust is keeping secrets.